Hi all, this is Mr. Yeager for chemistry. We are starting our unit on solutions. With solutions, this is a big unit. I know we've already talked about solutions once before, but now it's getting into more detail of how we're going to make solutions and all the things that go along with it, okay? Why is this so important? So many chemicals that we use basically to create products. So if we actually get into being a chemist or a pharmacist or chemical engineer, okay, we will be usually using solutions of chemicals to do these chemical reactions that we want. Again, it helps them go a lot faster so the products can be made. We can figure out what should stay dissolved, what should precipitate out, and then we can do ways to obviously separate the different parts. So that's why we are looking at this in such great detail. All of the chemical reactions that we've done in labs and everything that the teachers set up for you, we usually have them set up as solutions. And we don't just pour chemicals together and mix them up. We actually have to measure out a certain amount of each of the chemicals and the volume because we're looking for particular results for you to have in the end. And obviously there can be possibly a safety danger thing that can be involved if we use too much of a chemical. Okay? So what we are going through is we're going to look at what are solutions and analyzing solubility curves in this video. Then I'll do another video on measuring concentration, a separate video on solution stoichiometry, and then finally finish up with colligative properties. So that is our plan, and we are excited. Woo! Okay. So what we got is, okay, we've already talked about solutions before. We're going all the way back to Unit 1 where we just were like, let's just talk about matter, okay? And let's talk about that matter can be in the form of pure substances, it can be mixtures, all right, and so forth. But, you know, we're getting into more detail now. We don't need to worry about suspensions and colloids. We are strictly looking at solutions. And we already said, again, a solution is a mixture of a solute and solvent where you cannot see the separate parts of the mixture. The solute particles are so small, they are invisible to our naked eye, okay? They're pretty much usually too small for even a regular compound microscope, okay? So, to review again with this, what is a solute? A solute is the chemical that is dissolved. It's the one that goes into the solution, okay? And like I say, if we're trying to get confused, if we're getting confused about which one is which, it's what am I adding into the liquid or whatever that's already there, okay? That's my solute. You can see my picture up here. Basically what happens, and we'll get into this more detail below, is you dissolve this ionic compound. That's the green and yellow. The water comes in, and it basically attracts the particular charge of the particles that it's interested in, and it will surround those, and therefore you can no longer see it. The water is completely surrounding it. The solvent, that is your dissolving agent. Okay, what is the substance that is going to surround the solute? This is most of the time water, which is why it's called the universal solvent. And again, we talk about aqueous solutions so much, but we can have other sorts of solvents as well. Okay? So the process in that picture above is actually what's called solvation. All right? That is the process of the solvent surrounding the solute. Okay? That's just a fancier word for dissolving, but the official term for it is solvation. All right? So how do I know this will even occur? Okay? Well, we basically have a simple phrase. Like dissolves like. Okay? What does that mean? Like dissolves like? Well, this again brings us back to other things we learned. This is why we've held on to this unit till now. Remember polarity? All right? Determining whether the substances are polar or non-polar will tell you whether they will mix together, okay? Whether they will form a solution or not. So a polar substance dissolves polar, non-polar dissolves non-polar. Again, just as a reminder, polar particles, molecules are the ones that have a slight positive negative charge at either end of the particle. They are asymmetric particles, okay? They are asymmetric like water. Non-polar are symmetric particles, and therefore they do not create the poles. The electrons are all shared very evenly amongst themselves. But that is basically the idea. Well, how can I try to identify again polar and non-polar very quickly? Well, first off, we have to know water is polar, okay? So if something dissolves in water, that object that I dissolved must be polar as well, okay? So water is polar. Ionic compounds, we basically say are polar. And again, I know we talked about solubility rules and stuff like that where some things will dissolve better than other things, we will kind of generally use this idea that ionic compounds should dissolve. Okay. Again, it depends on what it's with. If there's something else that's with it, obviously they will combine and form precipitate. Okay. Ammonia, that's NH3. Okay. And again, I'm just giving you a few examples. If I give you another compound, I'm just going to write NH3 again. Remember, NH3 look like this. So we have the negative charge on the top, sorry, and then the partial positive on the bottom. But I could still give you other chemicals, covalent chemicals, molecules that you need to recognize as polar based on their shape. All right. Again, we're not going to get super complicated ones, but we should be able to identify what is polar. Nonpolar are mostly oils, and then these generally covalent compounds. All right. And again, I know I just maybe confused you there. You're going, wait a minute, covalent could be polar. It could. Most of the time in this unit, if I give you a covalent compound, it's one that is actually nonpolar. Okay, that's why I mentioned water and ammonia, because they're covalent, but they are absolutely polar compounds. Okay, and any oils, fats, you know, things like that, they're basically nonpolar substances. Whoop. Okay. This is just a neat picture, kind of a slow motion picture of oil mixing into water. So again, that's a polar, nonpolar, and that's not a solution. Some additional terms just to get as I continue to say them throughout this unit. Something that is soluble is something that can dissolve. More specifically, we use that term when we're talking about a solid or a gas. Okay, a solid or a gas. Something that is insoluble is a solid or gas that cannot dissolve. Then we use this other word, miscible, which specifically refers to liquids that can mix together and dissolve into each other. Okay. So that would be like an alcohol compound, which is a polar compound that could mix into water and therefore form a miscible liquid. Okay, a miscible liquid. Now, there's nothing wrong with saying soluble liquid. It's just, again, this is more kind of the technicalities behind it, where we use solid and gas as soluble. Liquid, we use the word miscible or immiscible. So oil is immiscible in water. Okay. And there's Spider-Man. Yep, just kind of something to throw at my students just to keep them paying attention. So solubility. Solubility, we will get into it. We'll do this a lot more in just a moment. It is the actual measured amount that can be dissolved at a particular temperature dissolved in. Okay, amount that can be dissolved. I guess I shouldn't say in at, but whatever. Dissolved at a particular temperature, pressure, and volume. Okay, of solvent, volume of solvent. All right. So, I mean, I think you guys can kind of understand this a little bit, and we're going to do solubility curves in just a moment. Okay. Obviously, if you have more solvents, if you have more water, we can add more stuff into it. Okay, we can put more particles into it. All right. And also, you probably already know this one too. If you increase the temperature of your liquid, you can usually dissolve the object. You can dissolve more of the object. You can also dissolve it faster. We're going to look at that in a moment. But we can get more of it in it as well. Pressure. Pressure only is talking about when we have gases that we're trying to dissolve. So we're talking about carbonation. Okay, talking about sodas with carbonation inside of it. All right. Obviously, at a high pressure, we can get those gases to dissolve in the liquid. That's why when you open a can of Coke, it hisses out, because the idea is you're dropping the pressure in the can very quickly, so those carbon dioxide particles are coming out of the liquid itself, okay, out of the solution. But temperature and volume of solvent are two that we're going to play around with quite a bit. And again, this is actually a physical measured quantity. We can say this much, 10 grams of sugar should dissolve in this much solvent at this much temperature, okay? More terms with all these trash cans here. What the heck are these trash cans for? Okay, and I might have to go back up. We will be describing solutions as saturated, unsaturated, and supersaturated. Saturated solution, and again, I hope you know some of these terms. You've heard it before. If something is saturated, it's basically covered. If you think of somebody like saturated in sweat, obviously they look like they're covered in sweat. The idea of a saturated solution is that we have completely maxed out how much can be dissolved in that solution. All right? You have basically reached the solubility. So you have added the exact amount that should dissolve in that substance at that temperature. That is a saturated solution. How do I know it's a saturated solution? Well, if you keep on trying to add any more of those salt particles or whatever, you keep adding more sugar, all of that will sit at the bottom. You can sit there and stir it and stir it and stir it and stir it, and by the time it settles, all that sugar will keep coming back down at the bottom again, okay? Or the hot chocolate mix or whatever, okay? It's a saturated solution. You can't get any more in it at that temperature, okay? Unsaturated would mean, as the name implies, not saturated, meaning we have less solute dissolved and we could put more into it. How do I know? I add a little bit more, I stir it in, and guess what? It disappears, okay? So again, those are the more common type. We have saturated and unsaturated solutions, which basically, I'm trying to show with like the trash can here, is we have a trash can that's completely full, and we have obviously a dumpster that's not full. I could keep putting more stuff in it. I shouldn't keep on trying to put stuff in this particular trash can. All right, those are your two more common types that we will manipulate more and more, okay? It'll be, hey, is your solution saturated? I don't know, what should you do? Add some more and see if it mixes in anymore. If it mixes in anymore, then yes, it was unsaturated and we should keep going. If it settles to the bottom, it's saturated, all right? Now, supersaturated is something that is not super common. Not me to say super, all right? It's something that we don't just all of a sudden can make it easily, okay? I think people sometimes think, oh, I could just keep adding more and now it's supersaturated. No. Supersaturated means is that there's more solute than should be dissolved at a particular temperature, all right? Now, this is something that you can't just make. You can't just sit there and be like, let me add some more and hey, it's dissolved. No, that probably means it's still unsaturated or saturated, okay? Probably unsaturated. What you actually have to do to make a supersaturated solution is you have to already know the solution is saturated, all right? Basically, the process is you heat up the water. Like this is how you make rock candy, essentially. You heat up some water, okay, at a high temperature, and you start dissolving sugar into it. We'll see in a moment, at a higher temperature, I could dissolve more sugar than at a lower temperature. What should generally happen is when I pull that pot off the burner and let it sit, as the temperature drops, I should actually start seeing crystals come out of that solution. All right, crystals should start forming from that solution because as the temperature drops, it can't hold all that sugar anymore. So usually, and this is where a lot of people don't do it right, that actually starts happening to them. That's not the rock candy. You're not making it correctly. All right? So we should have precipitate form. If no precipitate forms as the temperature drops, then we might now have a supersaturated solution. All right? The solution is now, Larry, you're like, I know I dissolved this much in it, and I'm not seeing any of it come out. You now finally have a supersaturated solution. Not many chemicals do this. Most chemicals will basically reach a saturation point. You know, you'll basically saturate the solution at that temperature, and then this will continue to drop, and again, what you'll see happen is little tiny crystal particles come out, and you'll start having more and more stuff on the bottom of the beaker. Okay, that would just still be a saturated solution. But one way you can kind of test whether it did actually become supersaturated is if you try to add any more solute, what will happen is all of a sudden a large number of crystals will form. So let's see if I kind of like draw a bad picture about this. So let's say you have a supersaturated solution here. Okay, supersaturated. What happens is you go ahead and bring a stick down with a little bit more sugar on it. So there's sugar at the end of that stick. You dip that into the liquid. What the liquid basically does is, I always kind of describe it this way. It's almost like the liquid freaks out because it's going, what the heck? Why are you trying to put more in? We already have too much. And what will happen is, all of a sudden, you'll see a lot of crystals basically start connecting to that little bit of sugar, and then you'll have your rock candy. You can pull that on out. So a large number of crystals will all of a sudden form from a little bit trying to be added into it. That is a supersaturated. So I use this last trash can as example, where it's like, this is not how this trash, that's the one on the right, that's an overflowing trash can. And the idea is, while people could go ahead and balance stuff on it, I always say this even though I don't see it at lunches anymore, like in high schools, but you know, people are always trying to keep on adding one more piece of trash because they don't want to carry it with them. But what can happen is you can put one more piece of trash on, and it destabilizes obviously the setup, and all of a sudden not just your piece of trash, but all these extra pieces of trash fall out as well. Okay, and so that would be kind of the same idea with a supersaturated solution. All right. What about what's going to affect how quickly something dissolves? I'm not saying how much dissolves. This is talking about the dissolving rate. There's 3 factors that will affect the dissolving rate. The first one we already mentioned, temperature. Generally, if I increase temperature, I should increase the rate of solvation. Okay, I should increase the rate of solvation. All right, that should say increase. Sorry about that. Okay, you can see, why would this happen? The particles are moving faster. They have more kinetic energy because there's more temperature, and they will go ahead and surround the solute a lot faster. The solute will also be able to find the solvent quickly, and that interaction causes dissolving. So increasing temperature increases the rate of solvation. The exception to this is gases. Gases, if you increase the temperature, will actually decrease solubility, and it's because they're already moving very quickly. What happens is you're increasing that temperature, and they can then escape the solution. Okay, it's more difficult for the solution, the particles, the liquid particles, to hold on to those gas particles. Surface area. If you increase surface area, you'll increase the rate of solvation. Again, why? You decrease the size of the particles. I don't mean to say that, sorry. The idea of surface area is there's more exposed. That's all I wanted to say. There's more exposed. You can see I have sugar cubes and then crushed sugar up here. The idea is if I put the sugar cube into the water, only the outside particles are exposed, and therefore it'll take longer for me to get down into the core of that sugar cube. Okay, it's going to take longer. But if I smash it, every single particle is exposed, and therefore it has more surface area, and therefore can undergo solvation quickly. And then, of course, stirring and agitating. Agitating basically means shaking. If you increase stirring, obviously you're making those particles move around more. You're increasing the ability for the solvent to surround the solute. So temperature, surface area, and stirring all increase the solvation. So it's a direct relationship between the two, except for gases. All right. One more thing on this page. Let's talk about separating out solutions. Okay. For separating solutions, we basically have 2 methods. We have distillation. Distillation, this occurs basically based on the boiling point of the substances that you have dissolved in the solution. All right? And so this is usually used for liquid-liquid solutions, where again you can have an alcohol and water. Usually, depending on the alcohol, it can have a lower or higher boiling point than water. And so this is kind of a neat technique. I've done this a lot of times, where basically you heat up the whole solution, and what will happen is some of the particles will start like heating up, and the ones that have the lower boiling point, yes, there will be like, so sorry, let me go back with this. So let's say like I have an alcohol and I have water, okay? And so water would be 100 degrees Celsius, and then let's say alcohol is 79 degrees Celsius is the boiling point. When it reaches 79 degrees, you'll see it start bubbling, and it looks like the whole thing is bubbling, and some particles, you'll see some vapor start forming. What will happen is you'll see it form, and you'll see condensation, and some of that will come back down. That's because some of the water will go up. But what will happen in the end is only the alcohol will reach all the way to the top here, and you'll see that this will reach 79 degrees, the thermometer. Like it'll stay at 79 degrees. And what will happen is when it reaches up here, it hits this tube and basically starts running down where it starts cooling, and then it'll change back into a liquid, and you can have the alcohol over there. The water should all return back down. What should happen eventually is you should see it stop boiling, and that means all the alcohol is gone. Now, if you let it keep going, the water will start boiling, and then it'll shoot up and over, and then you're making your solution again, so you do have to stop it eventually. Another neat method is chromatography, as I draw right through the word. Chromatography, that's where we can separate out, again, different parts of the solution. We use something called a mobile and a stationary phase. Usually a stationary phase is a piece of chromatography paper, and a mobile phase is some sort of solvent that can go through. It'll dissolve in this case, something like ink, and then it can separate out the colors based on what the substances are. Some substances can stay dissolved a little bit longer and will separate out farther along the paper. But, as Dikembe Mutombo says here, no, okay? Filtering will not separate out a solution. Okay, that is because you need solid particles. So filtering does not separate a solution, so we got to be careful with that. So distillation and chromatography are two methods there. All right? So a lot of terminology there, but we're going to cover one more thing. Okay? We want to look at solubility curves. Okay? So with solubility curves, these are graphs that are going to show how solubility changes with temperature. All right? There's a lot of things we can then do with this. We'll be able to use this to figure out how much can be dissolved, when is the solution saturated, unsaturated, supersaturated. How much, we already said that, how much can be dissolved at different volumes, so not just at one volume, and can determine how much can be added or precipitates when I change temperature. So there's lots of questions that we can do with solubility curves. So I have a giant one here, okay? Sorry, this is just a large graph. You can see temperature on the x-axis, solubility on the y-axis, and you can just, usually most solubility curves have lots of chemicals on it. And so what you can see here is most of the lines are going up, showing you as I increase temperature, solubility increases for all these different substances. Now you can see there is an exception here. There's this cerium sulfate, all right? Cerium, what is that, 3-sulfate? Cerium 3-sulfate there, all right? That actually decreases in solubility as the temperature goes up, all right? Usually that would mean that we could probably guess that's a gas. That's probably not a gas. I could tell you that cerium sulfate is most likely a solid, and that's just a weird solid that doesn't change. But different chemicals have different solubilities, and we can do a lot of different things on this, okay? One thing to notice that you need to read on the left, on the y-axis, is this is the solubility, and it's telling you in how much water, and that's going to be important for a couple questions we're about to go over. So I'm going to show you all the things we can do with solubility curves. Okay, so that's basically it here. I don't think there's anything else I need on this part. Oh, yep. Okay, so I have this one here that we can see a little bit better. Okay, and so let's go through basically the questions I can ask you. Okay, so let's just again go over what this means. So I'm going to look at NaNO3. So what this is showing you is this line is showing you the solubility of NaNO3 at many different temperatures, from basically 0 to almost 90 degrees, and then it's off the graph in this particular case. Okay, so again, we can see NaNO3 is increasing pretty well. All right, some chemicals increase more than other ones. You know, KNO3 starts very low, but look how steep it goes upwards. All right, if it's a steeper curve, its solubility changes more. NaCl here is a fairly flat line. It maybe changes about 2 to 3 grams max over 100 degrees. So regular salt does not change its solubility too much. Table salt, I should say. Okay, so that's something to notice. So some questions I can ask you is I could be like, hey, at 20 degrees and, you know, at 20 degrees, what substance is the most soluble? Well, what would I do? I'd zoom to the very top and go, Ki is the most soluble. Okay, what's the least soluble? At this time, it's just barely still this potassium chlorate. It's still just barely less soluble than the cerium sulfate. Okay, so I can obviously ask you kind of comparison questions and go, which one has the largest change? Which one has the largest solubility? Which one has the lowest solubility at those temperatures? Okay. Other things, I mean, common questions would just be, you know, how much NaNO3 dissolves at 60 degrees. Okay, how much dissolves at 60 degrees Celsius? Well, I would go to 60 degrees and I'd shoot up the line as straight as possible and go to NaNO3. And again, I would look for you just kind of to estimate this. I mean, I would put this maybe at what, like 124 grams. If you said 123, good. If you said 122, I'd probably still accept it, even maybe 125. Okay. Now, if you said 129, I don't know what you're doing. Okay, but 124 grams, that's pretty reasonable. Okay, we don't need to be overly exact, but we can tell it's somewhere close to that. Okay, as my line goes all over the place. So that's a quick question. I could say at what temperature does, you know, 80 grams of KNO3 will dissolve? At 50 degrees Celsius. So there's standard reading a graph analysis. Okay. Other questions I can ask. I can ask, Is it saturated, unsaturated, or supersaturated? So what I would do there is I'd go, okay, you have, I'm going to use NaNO3 again. You have 40 grams of NaNO3 at 40 degrees Celsius. Would this solution be saturated, unsaturated, or supersaturated? So I would go 40 degrees, 40 grams. I'm only right here. Where's the line for NaNO3? It's up here. The line represents the saturation point. So if I ended up on the line, or very, 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 very close to the line. Again, don't be like where you have to hold it straight up to your face and like get really close to look. If it should basically look like it's on the line, it's on the line, okay? That would mean it's saturated if it's on the line, But I'm clearly under the line at 40 grams, 40 degrees. Why would that be? What would that be? Well, that's unsaturated, under the line, okay? So unsaturated is going to fall under the line. If I said I had 130 grams somehow dissolved at 40 degrees of NaNO3 Celsius, NaNO3 Celsius, I can't, my brain's going too fast. 130 grams at 40 degrees Celsius, well now I'm all the way up here, and I'm saying this is actually dissolved. What does that mean? Well, I'm above what should be dissolved, and that is supersaturated. I always say it's flying over the line. If you're flying over the line with your data point, you're supersaturated. If you're under the line, you're unsaturated. If I said 105 grams got dissolved, well, guess what? That looks like it's pretty much on the line. So that would be a saturated solution. So I would give you a mass and a temperature and a chemical, and you would just have to find that data point, focus on the one line. I think that's like the biggest thing with these graphs. There's a lot of lines on here. There's a lot of things you can get distracted on. You just got to pay attention and go, I'm only focusing on the NaNO3 line, not the KNO3, not the NaCl or anything else like that. Okay? Now, probably, I guess you could say is the most difficult question I can ask would be something like you have a saturated solution of, I'm going to stick with NaNO3. You have a saturated solution at, we'll say 70 degrees Celsius, and then you lower the temperature to 50 degrees Celsius. I will say, how much will precipitate? How much precipitates? PPT stands for precipitate. Okay? What happens here is, like we talked about, if you lower the temperature, we are going to lower the solubility of NaNO3. So all of the substance cannot stay dissolved. It'll stay saturated, but some of it will crystallize and come to the bottom. So if I look at this at 70 degrees, I'm somewhere right around there. So I'm going to say this is maybe 133 grams. At 70 degrees, I have 133 grams dissolved if it's saturated. At 50 degrees, I have, I don't mean to make my life difficult, but let's say 114 grams. Let's say 150, make it a little bit easier. 115 grams dissolved. All right? What happens here is there is an amount that can no longer stay dissolved. And all I do is I subtract the two. So 133 minus 115 is 18 grams. 18 grams of NaNO3 will precipitate. Now, I don't think I then need to show you. I could do the opposite. I could say I have a saturated solution at 50 degrees. I want to increase the temperature to 70 and keep it saturated. How much should I add? Same thing, 18 grams. It's the difference between the two. Whenever you're looking for the change, you'd always do the difference between the two. We should not be doing addition at all, okay? I mean, I could even ask, you know, hey, I do have one more question, sorry. But I could ask, like, I tried to dissolve 100 grams of NaNO3 at 20 degrees. Will all 100 grams dissolve? The answer to that would be no. NaNO3 at 20 degrees only has what? About 88 grams that can dissolve. So what should happen? 88 grams will dissolve and 12 grams will go where? To the bottom of the beaker. Okay, we would have basically a beaker here. Most of it would dissolve, but I'd still have 12 grams of stuff at the bottom of the beaker, at the bottom of the solution. Okay? One more question. I almost forgot this one. That would have been bad. Is using the amount of volume of water that I have there. Now you can see it says 100 grams of water. This is the solubility for these substances in 100 grams of water. Let me make it very clear. 1 gram of water equals 1 milliliter of water. Okay, the density of water is 1 gram per milliliter. So that's really nice. We'll obviously stick with water, but 1 gram of water is 1 milliliter. So just be aware that I might be going, you have 200 milliliters. Well, I don't see milliliters on this, I see grams, but grams and milliliters for water are a 1-to-1 ratio. Okay? So the last thing I could do here is I could change the volume. And so what I'd ask, again, sticking with NaNO3, is I could say, hey, at 55 degrees Celsius, I have a solution. I want to make a solution of NaNO3, and I have 200 milliliters of water. How much can dissolve? Well, at 55 degrees, I purposely picked that because that's like at 120. I can dissolve 120 grams in 100 grams of water, or 100 milliliters of water. Well, if I simply double the amount of volume, what can I do with my solute? I double it. So I can actually dissolve 200, I'll write it right here, I can get 240 grams of NaNO3 in the solution. So it's always basically a factor. I'm going to give you, 200, 300, 400. I might do fractions. I might do 50 milliliters. I might do 25 milliliters. That would obviously divide by 2 or divide by 4. I could do it that way. But you find how much can be dissolved at 100, and then just find the factor of change that occurs. Okay? I don't mean to make it like a complicated thing. How much am I changing the water by? And there's always going to be some sort of, I don't want to say whole number, but 2, 2.5, 1.5, 0.5, 0.25. It'll be something simple that you should be able to recognize it pretty quickly. All right? So that is everything. Quite a bit introduction here, but we will be using the solubility curves a lot. I'm sure you will if you're not in my class, but it will work out very, very well. All right? Have a good one.